Okay. So good morning and happy Friday. I hope after this you get a chance, or maybe your last class, if this is not your last class, you get the chance to go outside and enjoy some of this glorious sunshine and warm weather. So before today, I forgot, today we're gonna segue to a little bit of a follow-on from our discussion about distribution families. And we're going to motivate something called moments, which is important for what's called parameter estimation, this finding of good substitutes for the population parameters. And it arrives upon statistics or functions over the data that you can actually measure and use as a proxy, a good proxy, and we'll talk about what good means for the unknown population parameters. Okay, but before we begin, excuse me, the usual administrative bits. The reading hasn't changed, and the written exam number 2, as I announced last on Wednesday, will be on Wednesday, the 12th of April, this coming Wednesday, and it'll be the same format, 24-hour take home, but this one, for this one, it'll be all in Jupyter. You'll be given 2 small data sets, and you'll be asked a series of questions about these data sets that you'll answer by doing some analyses. And so it won't be as involved as the projects because certainly you won't be given as much time. And it's just to assess stuff about the data science process, the analytics, and things like that that we've discussed. And I don't really do cumulative exam. I guess for this subject, in a sense, it's inherently cumulative because many of the topics that we've done since the first written exam kind of are the building blocks of things that we did since then. Okay, after today, we have 3 weeks and 1 day. So the semester is quickly winding down to a close. I haven't seen the registrar's announcement. It used to be an email about when final exams are for my classes. For whatever reason, it's typically 8 o'clock in the morning. I know that's not fun, but I have no control over that. And so our final exam will be a comprehensive analysis project. You'll be using all the material, including the new material on extraction of insights, particularly machine learning methods, in a comprehensive analysis problem. And you're given about 2 weeks to do that. So I'll be announcing it 2 weeks before the last day of finals, which should be, I think, about 2.5 weeks from now. And we'll be using the final exam period for doing presentations about your project, acknowledging that your project might not be done, doesn't have to be finished when you do the presentation, because I have no control over when the final exam is scheduled. And so what usually happens with that is you hand it in electronically on the close of business on the last day of finals. And that's the tradition I usually have. And so I'd like to do group projects, mostly because given the size of the class roster and the 2-hour exam period, it's impossible to fit individual projects into that 2-hour period. Another approach I've taken in the past in other classes is to require folks to record their presentation, whether you're a group or individual, and then randomly pick the many individuals who are going to be presenting that day, literally drawing names from a hat or group names from a hat. So that's coming up. It's not something you need to worry about now. But what I like to do also on the administrative slide is announce upcoming milestones. And so I'll certainly, once I know when the scheduled exam period is, I'll certainly have that information up on the admin's slide for each class meeting. Any questions? No? All right. So I found a new source for some dad jokes, and the more groans, probably the better the dad joke. So I thought I'd try them out on you before trying them out on my daughter when I go to pick her up. So which days are the strongest days of the week? What do you think? Yeah. Strongest days of the week are weekdays? Okay. Close. All right. Saturday and Sunday because the rest are weekdays. All right. Anyways. All right. So this next one, and I promise you this is the last one for today. Um, did you know that the first French fries weren't cooked in France? Okay. Yes. Yes, they were fried, but they were cooked in Greece. All right. See, there we go. So you're going to repeat that one. All right. It works in elementary school. By the time they get to middle school, it's not a good scene. They don't appreciate them like they do in elementary school. Okay. All right. So where we last left off, we talked about, among other things, the normal distribution, and I have made a lot of changes to the slides late last night and early this morning. I always practice what I learned in industry, Kaizen or continuous improvement. Because on Lab 9, we talked about distribution families and summary, I decided to trim that material. And I also made some corrections between this version relative to what's on the Canvas site. So I'll certainly upload a new version of the PDF once I get back to my office. But where we last left off, excuse me, we talked about the normal distribution, and we said this distribution is very good for modeling physical quantities, things like temperature, pressure, position, velocity, which are also inertial. Their future value, if you take repeated measurements in time, have something to do with the current value within some small instant. And so the expectation, we said, the summary statistics of the normal distribution, the classic bell curve, due to its bell shape, is mu, the mean, and the variance is sigma squared. And these are the population mean and the population variance. And we said, for reasons for interfacing well with quantities measured from the real world, this normal, or sometimes it's called the Gaussian distribution, depending on which sources you read, it's very, very important because it's so widely applicable. We talked about the so-called standardization process, and this represented a transformation of measurements from or governed by a normal distribution. And this transformation requires you to do two things. First, you subtract the mean of all of your measurements from each of the individual measurements, and then you take that result and divide by the standard deviation. And for each original measurement x from a normal distribution, it gives you a corresponding z-score, z, from a so-called z-distribution. And when you do that, this z-distribution is a special case of the normal distribution, whose mean is 0 and variance, and therefore standard deviation is 1. And so this standardization process does for the normal distribution what percentages do for proportions. It sort of shrinks everything down, registers it on the same scale, so you can make comparisons between normal distributions that otherwise would have had different variability. And so an example of why standardization or converting to the Z distribution is important is, suppose you are measuring or comparing two temperate zones, right? You have some temperature measurements for one location, like Worcester in the spring, and then you have some measurements for, say, Montego Bay, Jamaica. And so with that, one of the things you'll notice, Worcester in the spring, the temperature difference, which you're witnessing, is very, very broad, right? It might be 28 degrees in the morning, and then yesterday as high as 70 degrees in the afternoon. And so if you have two systems and they're highly variable, one is more variable than the other, even if they're both normal distributions, it's hard to make a comparison between measurements because these differences have a different meaning. In Montego Bay, Jamaica, in the spring, the temperature doesn't vary as much as it does here in Worcester in the spring. And so if you are talking about my temperature increased by 5 degrees, if your temperature swing throughout the day is 30 degrees in Worcester, that 5-degree difference doesn't mean the same as a 5-degree difference in Montego Bay. And so this standardization, similar to what percentages do, it allows you to talk about distributions on the same scale, It's a really important mechanism for making comparisons. Because if you compute something like a correlation to look at the linkage between two variables, it's not a fair comparison if the variability of one is much bigger than the other. And recall, the correlation is the covariance divided by the product of the individual standard deviations. If their deviations are different, it's not going to give you fair results when you're measuring linkage. Okay. Any questions? Does that make sense? Okay. And so this standard normal is also useful for so-called outlier detection. And the question that outlier detection answers is this measurement typical of a population of measurements that you've collected? And that's useful for a whole host of things, including spam detection. If you use something like Gmail, or I don't know if anyone still uses Yahoo, but Yahoo Mail does it too, you'll notice that it automatically categorizes your emails as being spam or atypical, right? And so what's happening underneath the covers, it's building a huge distribution of all of the word occurrences that can happen in email, both across your email inbox as well as the population of others who use the product. And then when a new email comes in, it tests it against what is typical using a form of the same type of outlier detection. It's just a different distribution that uses multiple variables. And so with it, it says, okay, well, this is atypical, where typical statistically is measured as being outside of 95 degrees of the probability mass. And statistically, 95% is considered a short. They always allow that 5% for a little bit of variability. Okay. Any questions? No? Does that make sense? All right. And we had some examples with the Halter monitor I discussed and with the physical therapist in a box project. And so, I already said that. And lastly, our last tool that we talked about is probably the most important result from a standard probability course, and it's the central limit theorem. And we saw examples of that in the lab session on Wednesday. And it says that as long as you transform measurements from a distribution, and that transformation involves a sum, it doesn't matter what distribution that those measurements come from. If your sum has enough or a large enough number of terms, and it differs depending on the distribution, that distribution, when you transform it, it all becomes a form of normal distribution, which is really important. So you could have a Poisson distribution and a normal distribution, or Poisson and a gamma distribution governing variables in your measurement, and you can transform them both to normal distributions, and then you standardize them both to become standard normal, and this allows you to make correlations between measurements, even though they started out as being entirely different, governed by entirely different distributions. Does that make sense? Any questions? All right. And in the standard undergrad, well, I really don't know how it's taught here, but in a standard undergrad probability course, they would actually hopefully do the proofs for the central limit theorem and show you where it comes from and why it works. Okay. So one of the examples we gave is, suppose you had your customer arrivals in your system. You operated, say, an ice cream shop, and you enterprise to figure out what the relationship is between the temperature and the number of customers, the demand that you have coming into your ice cream shop. And so you could certainly instrument the entry box with an overhead camera, counting the number of customers that arrive in time. That's well modeled by Poisson, those measurements, Poisson distribution. And then the temperature, it's inertial and it's a physical quantity. That's well modeled by a normal distribution. And so you take the average temperature in windows of time. You take the average number of customer arrivals in from data in windows of time, and then you standardize these averages where each measurement is an average, no longer a single measurement from its native distribution. And then you standardize to get a Z distribution, and now you can measure the correlation between the average customer arrivals and the average temperature. Does that make sense? It's an immensely useful tool. All right. And you've seen that it actually does work on the fifth project assignment that was submitted. Okay, any questions? No? Make sense? All right, to jar your memories. And so we're going to refer to a topic that's pretty important in data science. It's inference. And inference allows you to ask questions about your system by choosing a model like Poisson for customer arrivals or normal for temperatures. And then you ask this model, this mimic, if you will, questions. And the reason why someone might want to do that is because you want to be able to infer or figure out or make an quote unquote educated guess about what the future behavior of your system might be. So if you measured the customer arrivals each week for your ice cream shop for every hour of operation over the course of a year, now with all this data, you choose granularity for representation. Maybe you have a Poisson for each day, Poisson for each week. And now, given that real data, you can produce samples or fake customer arrivals and then ask it questions like, can I afford to hire a certain number of employees? And so you can also track the amount of money that's spent every hour and then do a really precise simulation that you can use to ask about the revenue that you're going to take in and answer such questions. And so this inference is a really important part of data science because it allows you to pose scenarios rather than trying it for real with your ice cream shop and potentially going out of business because you had 10 employees on staff for the day when you only needed 2. Okay? All right. Any questions? No? And the nice thing about these models, it allows you to observe any seasonality. Perhaps in the summer, height of summer, when the correlation is high, I'm sorry, when the linkage between temperature and customer arrivals is high, you notice that your revenue has a certain profile. And you can absolutely simulate all of these things instead of damaging your enterprise by trying it with the system before you simulate it. So this inference is a really important aspect of data science. And so the question then is, what exactly is this inference more formally? And let's recall, we talked about this idea of a population, and we used the homeless population as an example. And we said all the values are governed by some distribution, but you don't have access to the parameters that control these distributions. And so if it were something like the customer arrivals in an ice cream shop, you have no idea, nobody does, what the ground truth lambda is, right? You don't have access to that. But what you do have access to are the samples, all of those measurements that you can take in from the overhead camera or maybe some thermometer that's connected to a computer. And you can then take these measurements and compute some function, a statistic. Now, there are special statistics, so-called estimators, and that's the focus of what we're going to talk about for inference. And so these estimators are so-called good replacements for these unknown parameters. And so theoretically, these parameters are often called theta in the statistics literature, and you might have a bunch of different parameters for different aspects of these distributions that govern your values you're measuring from the population. And so whenever you see the so-called population parameters, which are hidden from you, and of course in project 5, showed them what you are, we showed you got to see what they were because you needed to measure this idea of convergence between the population version of something and the sample version. But nonetheless, when we talk about the population parameters in the literature and statistics, it's often called theta is the population parameter. And then the estimator version usually has this hat on here. So theta 1 hat is the estimator or the replacement that you're enterprising to use, the replacement for theta 1. Okay, just some notation. Any questions? Does that make sense? All right. And so here, the estimators, if they're quote unquote stable, then they are reasonable replacements, good replacements about this unknown quantity. And what you saw, one aspect of doing inference, as you increase the sample size, your proxy from the data became closer and closer and closer, and sometimes exactly equal to the unknown population parameter. And so this idea of what is a good replacement is part of inference. And if your estimators are so-called stable, and we haven't defined what stability means statistically, we'll get to that in a few slides. If they're stable, then yes, they are good replacements for this unknown quantity, stressing that you don't get to see the population parameters. But you know that if you create a statistic that has these properties, it's going to be very close to what this unknown is. And that's a rigorous proof. So when you have these estimators in practice, if you're going off designing your data set through something like survey design, it's going to save you a lot of time, effort, and money. And the example we gave at the beginning of the semester is if you wanted to know, for example, the average age of a member of the homeless population, you'd have to hire thousands of social workers to go out and contact members of the homeless population in order to find out everyone what it is. But municipalities have fixed budgets, and it's really expensive to hire social workers, right? And so this idea of these stable replacements, it also not only do you not have access to the population parameters, ground truth, these estimators save you time, money, and effort because you can take a finite number of samples and you're guaranteed it's going to be close enough to this unknown to which you don't have access. Okay, any questions? Does that make sense? No? All right. Now, remember when I first learned this, it's like, wow, this is creepy. And it really works. The only difference is how big the sample size should be and how many terms the sum should be. So instead of this, you're dealing with your estimators. And you have exact control over these statistics because you define the function over the data. Okay, that's convenient. So every statement that we make using the statistic about the underlying population, when we ask it questions, when we simulate it or model, it applies very well, sometimes precisely, to this unknown. And I think that's pretty amazing. Hopefully, you appreciate that as well. And so suppose, and this is an example, we're dealing with customers arriving at the store. We instrument this, and I think I've shown this before, a tracking system. And this tracking system is just counting the presence of customers. It's not looking at their identities. And you can see that it's the numbers in the upper right-hand corner corresponds to the number of people who have entered the store and the number of people have left the store. And so absolutely using a Poisson distribution assumption, you can actually use this arrival data. This many people entered the store over this unit of time. And the difference between how many entered and how many left, that's the number of people in the store. And in modern commercial enterprises, they usually have computerized point of sale systems. So you can also track the amount of money being spent during each period of time. And so you have all of the data you need in order to simulate or forecast the amount of revenue that your enterprise will bring in over periods of time, all the data you need. And so this idea, then, we know for customer arrivals, it's well defined by a Poisson, and we know the parameter for Poisson is the average rate lambda. And I'll just sort of, like the cooking shows, give you the answer, and then we'll fill in the related background information and the methods that go along with how these answers were produced. And so it's widely known that the sample mean, X bar, is a stable estimator for the population mean, right? That's a rigorous result. And that comes from some methods that we'll talk about probably, I think, in the next module, hopefully on Monday. Okay, any questions? Does that make sense? All right. And so if you knew that this sample mean is a stable replacement for the population mean, well, we know the population mean is lambda, so we can just, instead of trying to guess at what the correct lambda should be for this tracking data for customers for the store, we can just measure the sample mean, X bar, the number of customers per unit time, and then just substitute this X bar for lambda. Now, what does this do for us? Okay, so now our mass function for the Poisson becomes e to the minus X bar times X bar to the X power upon X factorial. And so literally everywhere we see this lambda, we're going to replace with the value X bar. As easy as that. Any questions? Does that make sense? All right. And so with this information, now that you have a mass function, you can now ask the Poisson distribution with this X bar value, substituting lambda, you can ask it questions. You can ask it to give me some customer arrivals. You can now evaluate probabilities. How likely am I to see 5 people come into the store during this unit time? And it's the asking of these questions is the inference. You're using the data that you have to mimic the distribution whose parameters are unknown. And because we are familiar now with distribution families, you can make various modeling assumptions based on properties of the system that you're trying to simulate. Okay. Any questions? Does that make sense? All right. And so this begets the question of what exactly makes something a quote unquote good replacement. Okay. We talked about stability. And when I think about this word stability, I think about 2 types of things. Suppose you're walking a tightrope. This thing does not sit still. It moves, but it moves in a way that, on average, it's kind of in the middle, right? Might move a little bit to the left, might move a little bit to the right. But on average, these different configurations, these different values, it kind of averages out to being right in the middle, which is kind of this perfect value that you want if you're trying to walk this tightrope. Another thought about stability is a bridge. This thing doesn't move very much. It's there. It doesn't move. Well, technically it does a little bit, but it's there. It's very rigid. It doesn't move. The bridge doesn't shift too much. It's very, very quote unquote stable. And so this idea of stability in these 2 visual examples, it's reliable. You can count on it. You can jiggle the value a little bit, change it, and on average, it gives you exactly what you need. Okay, you saw that on project 5. You saw sometimes the value for the average is a little bit bigger than ground truth, sometimes a little bit smaller. But as you increase the sample size, on average, it gave you exactly what you need. And so this bridge is kind of like something called firmly established. It doesn't move very much. It's this rock, so to speak, that you can count on. And so when something is reliable, it's not likely to fail. And when it's firmly established, it doesn't change very much. Now, in statistical speak, this first one is this test for what's called an unbiased estimator, an unbiased statistic. And we have rigorous definitions for what unbiased is. And this next thing, firmly established, it's consistent. It doesn't change very much. Now, this last one is directly related to what you probably observed on Project 5. As your sample size got really, really big, eventually it didn't change at all. Okay. So you give it all kinds of data. You can give it typical values, you can give it outliers, and if you measure it enough times, on average, it's going to be exactly what this unknown was that you were looking for. That's what unbiased means. Consistency says if you give your estimator, your statistic that you're enterprising to use as a replacement for your unknown, if you give it enough measurements, like increasing the terms in the sum, it does not change. It'll just stay right on one value and not change very much. Any questions about this? Does that make sense? Okay. And so the proof that you'll find in the stats course, whether or not a statistic or an estimator, and what makes a statistic an estimator is that you're proposing to use it as a replacement for an unknown quantity from the population. And so for an estimator, there's an assumption. There's that independent and identically distributed assumption. And so if you take this variable governed by some distribution and you measure it again and again and again and many times, each time you measure it, it's from the same distribution. So you're not going to measure the temperature in Worcester now and then tomorrow the temperature in Montego Bay, Jamaica, right? That's not identical in terms of the distribution because these 2 distributions have different means and variances because they're 2 different locales. So the requirement for this idea of unbiased, it's a litmus test, and it's a test to see if this property holds true. But in order to evaluate that property, there are certain assumptions you must satisfy, and that's what this IID does. It's the assumptions you must have true. So it's independent. One sample does not influence the next samples in this sequence of samples, and it's identically distributed. They're from the same distribution. Okay, any questions? Does that make sense? All right. And so if you have IID samples and this index represents the sequence of samples you're taking, the measurements, if you have some statistic that you're going to measure over that window of n many measurements, it's quote unquote unbiased, it's reliable if when you take the expectation of that function, that statistic, like x bar, the sum of those values divided by n, it's exactly equal to that population parameter. So that's what unbiased means. The next one, or if you're doing the proof, oh, I just lost my place. S squared. Okay, yes. An example of that, the so-called sample variance, and the statistic is typically noted as S squared. It's a good estimator, an unbiased estimator for sigma squared, the population variance. And you can actually do that by proof. You can take the expression for the variance. You can take the expression for the sample mean and the sample variance. You can compute the expectation, and it'll get you exactly the population mean mu and the population variance sigma squared. Okay. But we're not going to do that proof. I'm just making you aware of it. There's lots and lots of literature online, both in publication format as well as videos that will go through the details of that proof. And so the sample mean, you can also prove X bar is an estimator. It's stable for the population mean. So if you took that function for X bar, the sum of all the values divided by the number of values, and did the expectation, it's going to give you exactly back the population mean. And so that's one litmus test that talks about stability. The next one, consistency, refers to the number of samples that you have. And so the consistency litmus test for being a good replacement for the population quantities also makes that ID assumption. It's very important. And it says that if you have some statistic, your estimator, your function over data, x hat, theta hat, that if you increase the sample size, n goes to infinity, and it doesn't tell you how big it should get, but if you increase it, the probability that there's going to be a non-zero difference between the population quantity and this estimator is going to go to zero. And what does that mean? You make the window size big enough, and you saw that with Project 5, and then eventually the statistic is exactly equal to the population quantity, which is unknown. But in Project 5, again, I'll stress that the only reason you got to see it is so you could actually measure it and prove to yourself that this really does work. Okay. Any questions? Does that make sense? Okay. And so how would you prove that? Well, you would prove that your statistic approach is equal to the value in the large sample limit. And it's a standard proof that you get in an undergrad statistics course. Okay. Any questions? No? And so the sample variance, S squared, is a stable replacement, and X bar, the sample mean, is a stable replacement. It passes the consistency test. But if you were to look at the biased test or unbiased for the variance, the sample variance, you'll notice that the leading coefficient, if you use the version that's 1 upon n, it's going to be biased. And so they correct for that. And you'll notice the so-called unbiased sample variance has a leading coefficient of 1 upon n minus 1. Okay. And if you did that proof with the sample variance, it's fail the test for being unbiased. Okay. Any questions? All right. And so there are two, not just two, but two of the very popular procedures for creating these statistics that are both unbiased and consistent. There are two methods that we'll talk about, something called method of moments estimation and max likelihood estimation. And so it's called estimation because it produces for you a function over data, a statistic, and these two procedures guarantee that unbiased and consistent are going to be passing tests for the resulting functions. Okay. Any questions? All right. And so when you read the literature, sometimes you'll see the term a method of moments estimator or a max likelihood estimator. That's the result of the procedure, but method of moments estimation, max likelihood estimation is the process that you go through in order to arrive upon this statistic. Does that make sense? Okay. And so that begets the next question. Well, what exactly is a moment? Hmm, That's a great question. So I thought it useful to give you a little background behind what a moment is, because it's a general framework for how you describe the shape of distributions. Okay? All right. And so, I played in the jazz band in high school. I still play bass guitar. And so I always think that music has messages about all sorts of stuff. And so I'm going to play a song, and this is At This Moment by Billy Vera. And bass is, you don't have the rest of the band, but you can kind of pick out, the bass riff out of things. What would you do with this moment? You'd estimate things. That's what you do. Dum, 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 dum. Dun, 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 dun. Dun, 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 dun. Boom, 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 boom. Do, 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 do. All right, that's enough of that. So when all of this stuff was being developed, at the time, the tools they had were the tools from physics. And so people like not reinventing systems. So they try really hard to use the existing mathematical tools and other tools that they have at the moment. And so we'll go to the physics, and in physics, a moment is the combination of a physical quantity, a force, and a distance. And a moment is a force at a distance. And you might ask, well, Holness, why the heck should I care about that? Let me tell you why. What this force at a distance allows you to do is effectively multiply the impact of the force you're applying. Whenever you turn a nut with a wrench, you're taking advantage of moments. If you were to try to turn this screw, the rotational force or torque of your hands is only so much. But when you put it at some distance from that pivot point where you're applying that rotational force, now, depending on the distance, it multiplies your force. And so it is a tool that allows you to be a force multiplier. And so the development of tools is entirely useful because of this idea of a moment in physics. Okay. Any questions? Does that make sense? Now, why do we care? Well, let's take a look at the following scenario. We have a board, and in the middle of this board is a pivot. And if you apply a force on the right side of the board, it's going to want to turn. You get a torque going to the right, clockwise. And if you put a force on the left side of the board, your left, you're going to get a torque in the other direction, anti-clockwise. And so the torques applied at the pivot is dependent on this lever arm. And so what we really want is to analyze what is the net torque rotational force afforded by placing a weight on the board. And so what you do, okay, you add up the moments and you sum them together, and the result will tell you what the net force is. Now, some forces want to turn this thing, rotate it clockwise. Some want to rotate this system anti-clockwise. And so here we have a 10 Newton force, 2 meters in the negative direction from the pivot, and we have a 20 Newton force, 1 meter in the positive direction from the pivot. And so if we add this up, what do we find? We find that our 10 newtons at -2, that's negative 2 times 10, negative 20. And then we add to that the other moment contributed by the weight on the right-hand side. That's +1 times 20. That's 20. And you notice here, the sum of the moments is 0. And when the sum of the moments is 0, in robotics, we call this wrench closure. The sum of the forces and the sum of the moments is 0. And we get balance. The system does not move and it stays there, right? And so in statistics, a moment is used to measure the shape of a distribution, the shape of all of the points, the so-called mass points associated with a distribution. And so this is a distribution, and it also works in the continuous case as well. And we have along the horizontal axis all of the support set, the values over which this probability is defined. And then we have on the vertical axis, we have the probability associated with each one of our mass points, these black dots. And so each measurement has a probability mass of a certain size. And so we can imagine these are masses, and as masses, due to the acceleration due to gravity, another physics analog, it's going to exert a weight. And so let's depict the weight, which is a force in the downward direction, as an arrow. So the greater the mass, the larger the arrow, these vectors, right? That's directly proportional to the probability mass, okay? Now, more mass means a bigger force. And if we imagine then these forces are weights along the horizontal axis, imagine if we selected a pivot point, just like we had in the other example where we talked about moments. Well, let me ask you, if these x values, x1 through x8, if these are samples, what is that point where the pivot is right now, the blue? It's right in the middle, right? What point is that? What value is that? The middle order statistic. It's the median, right? So all the median is just that midway point by rank for all of your values, okay? Now you can compute a quantity by treating these probability, these mass points, as forces, and you can sum the moments together just like we did before. Now, when we do that, just like from the physics, we take the distance from the pivot and we take the amount of force, we multiply them. So we have this distance that x5 has times the force, this distance that x6 has times the force, this distance x7 has times the force, etc. All of those points to the right of the pivot, they want to exert a force, a torque, that's going to cause the board to rotate about the pivot in the clockwise direction. Well, is that clockwise? In the clockwise direction. I still have to do that. And then those mass points on the left-hand side of the pivot, those moments want to exert a torque or cause the board to turn in the anti-clockwise direction, right? So if you sum these moments together, it's going to tell you something about which way this proverbial board is going to move, okay? Well, why does that matter, okay? Before we talk about why that matters, let's consider a different pivot point. Suppose we located the pivot in this yellow position, and we found a place along the board such that when you put these forces down on the board, it balances directly. The sum of the moments is zero. It balances. That particular pivot point has a special name. That's the mean. And the reason why the mean in the literature, sometimes called the center of mass, is because it's the center of where these moments even out. Because the masses, the total mass in the left side, the total mass on the right side, they balance out with respect to that force at a distance. So it's sometimes called the center of mass for that reason, or the central tendency, if you think of it from a data perspective. And any questions about this? Does that make sense? Okay. And so now, oh, I already said that. Let's get back to the values that we can sum by adding up the moments. Now, suppose we use our pivot at 0, and we have, in this case, all of our measurements training off on the right-hand side of this pivot. If we were to add them up, yeah, we could have force times the distance, but there's a problem here. The problem is that if we were to take these mass points, and what if we shifted them to the right some amount? And so everywhere we saw x1, we had 2 plus x1, 2 plus x2, 2 plus x3. There's a problem with summing these moments together at that balance point. The problem is that the value changes. So that doesn't help us. The mass points in terms of the probabilities, that hasn't changed. The forces haven't changed, but the sum, it does change just by shifting it. So that's not very useful to us. So what if we did the following? What if we shifted that pivot so that the origin is at the center of mass among all these mass points on the board. Okay. This is called shifting the distribution so that it's so-called centered about origin, right? The center of the distribution, the center of mass of this system is now over the origin. Does that make sense? Now, with that, it doesn't matter what these values are. You now have a single value that does not change as a result of the relative size of each of these mass points. And the relative size of each of these mass points is the shape of the distribution. So then we take each one of our individual mass points, we subtract from each one the center of mass, x bar, and that is a centered version of this distribution. Does that make sense? Any questions? No? All right. So we don't care about the direction if it's centered. All we care about is the magnitude when we're talking about these distances in some cases, and I'll elaborate on what I mean by that. So we can then square it, okay? And if we square it, we're adding up these magnitudes. And now, if we want to make it a moment, we said we take the distance from the pivot. If it's centered about origin, we now take the distance between it and some value, and we multiply that distance, if we're talking about moments, we multiply it by the force. And the force, we said, is the probability mass, which is just the function f, our probability mass function, for each one of those measurements. Does that make sense? Any questions? All right. So more generally, we have what's called the nth moment. And the nth moment talks about summing together the individual moments. We have the measurements x, and we subtract off some quantity we'll call c, and depending on a host of considerations, we'll exponentiate it to the quote-unquote nth power. And then we multiply by the force. So here we have a sum in the discrete case, integral in the continuous case. We have a force at some distance, wherever you centered your distribution, and then we raise it to a power. Now, if that power is n, that's the so-called nth moment. And it's the nth order method for measuring the shape of this distribution. And it follows from the physics, because those were the tools at the time, and they reuse these tools to talk about this idea of the shape of a distribution. Okay, and so when you center at origin, this value you subtract is mu, but it doesn't have to be mu in general, but centering about origin, the C value, the centering value is mu. Does that make sense? Now, if it's non-centered, the C value is 0. And you can still compute the first moment, the second moment, the third moment. That order of the moment is just the value of that exponent. Does that make sense? And any questions? No? And so the mean, we talked about the central tendency. The mean is nothing more than the first moment that's non-centered. If you think about what the mean is, it's x bar. We said x bar, more formally, the first moment that's not centered is equal to the sum of all the values, xi, times the probability of that xi. Here we have the first exponent, 1, the 1th power. We have xi minus c, where c is equal to 0. It's non-centered. And then we multiply by the probability. That's exactly the sample mean, or the mean mu. So the mean, the central tendency, is the first non-centered moment. When we look at dispersion, we call it variance. The variance is nothing more than the second centered moment, where specifically it's centered about origin. Recall when we talked about variance, we said the variance of some variable is equal to the sum, and we said xi minus mu quantity squared times p of x I. Okay, well, we have the distance from the center, so that centering value c is mu. We have the second power, and then we have the force at the square of the distance from the centered version of the distribution. So another way of writing the variance is the second centered version of our moment. Okay. Our third moment is very useful, and that measures skewness. And so skewness is a measure of how lopsided your distribution is. From the physics example, skewness talks about which way this board is going to tip because the moments are not symmetric. There's more moment contribution on one side of the pivot than the other side of the pivot. And so it has a direct analogy to this idea of the sum of the moments is non-zero, and therefore your board is going to tip. Now, from a statistics standpoint, what that tipping means is it's going to prefer certain values more than others. When you tip to the high side of the pivot, you're going to prefer in your distribution, when you sample, it's going to give you more values that are higher. When you tip on the low side, on the other side of the pivot, it's going to give you values that tend to be smaller, right? And so this idea of the third moment, the third centered moment, centered about origin, measures the asymmetry or the lopsidedness or the skew associated with your distribution. And so this last one, and there are higher order moments beyond the four moments. They don't have application here. It measures more subtle, longer ranging changes to the shape of your distributions. But usually they talk about the first four moments in most analysis problems. The fourth moment, centered about origin, again, this power n is 4. That's called kurtosis. And it's a measure of flatness of your distribution. Or sometimes in the literature, they say Gaussianity. How much does it look like the Gaussian or less like the Gaussian? And so with that kurtosis, you have x minus mu to the fourth power times your probability. And so what it allows you to do, just like how the variance calculation, the second centered moment about origin, it allows you to compare two distributions, and you can say this is more unstable than that because its values wiggle more. In similar fashion, if you had two distributions that were left skewed or right skewed on the high side or the low side of the pivot, now you can make comparisons. Which one is more skewed, this distribution or that? That's what this third moment gives you. And likewise, which one is more flat? It allows you with specificity to quantify these quantities or these aspects of shape of your distribution, and now you can make comparisons between them. Does that make sense? Right, any questions? No? All right. And so method of moments estimation uses moments, so I thought it valuable to talk about moments, and it has a procedure for what you do with the moments. There's the so-called population moment, and there's the equivalent sample moment, and we'll talk about how you use them to arrive upon a statistic that is stable. Okay. Any other questions? No questions? No? All right. And so let's look at the third moment, and we're going to use the physics example, but if this were a statistics example, these weights would just be the probability mass associated with the values corresponding to where they are placed on the board. And so here, let's imagine we were computing skew, which is a measurement of lopsidedness, and it's centered, the third centered moment. And so here we have a weight of 10 newtons on the left side or negative direction of the pivot. And then we have a weight of 20 newtons on the right-hand side, 1 meter away from the pivot. It's distance. So if we added this up, third moment, we have 2 to the 3 power, that's -8 times 10. We get -80 contributed to the moment, some of the moments by the left-hand side. And then we have 1 to the third power, that's 1 times 20 is 20. So we have -80 plus 20, which is -60. So this says that it's skewed in the left-hand direction. Now, certainly you could construct a probability distribution and compute the skew, and it'll tell you both the direction in which that skew is, but also the magnitude of that skew, so you can make comparisons. Any questions? No? All right. In this example, we have two weights that are the same, so the same probability mass, but the values are different locations. We have 2 meters from the pivot in the left-hand direction, 10 newtons. And we have 1 meter from the pivot in the right-hand side of the pivot, the positive direction, 10 newtons. And so again, we compute our skew third moment centered. So that's -2. Oops, what just happened? -2 times to cube times 10. So that's -80 plus 10 contributed by the right-hand side. That's -70. So this -70 is more skewed to the left than the previous example, which was -60. Right? So you can make those comparisons. All right. And then lastly, let's say we have 10 newtons on both sides of origin, and it's centered about origin. And we'll, again, compute the third moment. So that's -1 times 10. That's -10 plus +10. That's 0. And so this is a symmetric distribution because the skewness is 0. Does that make sense? Any questions? No? All right. And so that's all I had to say. And next time, we will pick back up on Monday with method of moments and max likelihood estimation to actually show you the procedures that give you these estimators that are proven to be stable. And so the work was done for you with method of moments estimation and max likelihood estimation. You go through that process, and the resulting function over data statistic is a good replacement for the unknown population parameter. Knowing that statistic, you then implement it in Python, calculator over the data that you have, and then replace it in your distribution. So you wouldn't have to say Bernoulli P. You just say, what is my estimator for Bernoulli P? And then you just go ahead and sample from it like you did before. And so that closes the loop on some concepts that we went over in project number 5, or concepts for project number 5. Does that make sense? Any questions? All right. So that's all I had to say for today. I hope you have a glorious weekend. Get some sunshine, go outside, enjoy this good weather. And if you celebrate Easter, happy